the two things that we're going to really consider in this class was, the first one was, how fast, right? And so that's the derivative. How fast does something change? How does y change with respect to x? Now the second question in calculus is how much? How much do you accumulate? And so if we look at the answer to how fast, we look at the rate of something, which is the derivative. If we're going to ask how much, we want to total up something, and so we're going to use the integral to accumulate that. So how this relates to our look at functions and things is that we want to find areas under curves. And so in the most simple sense, if we have just the basic rate times time equals distance equation, okay, this is, you're going 60 miles an hour for 2 hours, you're going 120 miles kind of a deal. If you make a graph of it, of the rate times time, that area, the kind of green-yellow area there is really what you're calculating. And so when we have straight lines, where we have triangles or rectangles, things like that, we just take products of things. But what is a more difficult question is, what happens when the rate is varying? And so that's where we get into calculus. And so we want to calculate areas under the curve. And so there's a divide and conquer kind of mentality that you can use. This particular curve is x squared. Okay, so even though the scale's on there, I kind of exaggerated a few points of interest here. So, when we have x equals 2, y equals 4, and so on. So if we want to find the area under this curve, we can divide it into these strips and then say, okay, we have these 4 strips, and we're going to calculate the area of those 4 strips and say the sum of that is going to be the area. And so with my function f at x equals x squared, I want you just to take it on faith for now, because we're going to do some approximations of it, that the actual answer is 8/3, 2.67 or 2.6666 kind of a deal. So I'm telling you the answer before we go, and this is kind of the basis that we're going to set up what an integral, or how we can calculate an integral, is that we're going to look at the sum of these strips, the areas of these strips. Okay, so recreate my little curve here. Now, let's say I can't really calculate those strips because it still has that curved top. Now we can make an estimate of those areas by saying, okay, I'm going to take the left side of these intervals, and so this last interval I'm going to take f at x at 3/2, and I'm going to set up these rectangles, and here, f at 1 equals 1, and so I'm going to take the area of this as being, the width here is 1/2, the height is 1, all the way down to this one where if I look at the left side of my interval, it's 0, and so I really do have a rectangle here, but it's of 0 height. Okay, so if I calculate those, that's easy enough to calculate, right? I just take 9/4 times 1/2 and do all this. So I'm going to use those points, actually 4, you'll see the arrow coming in a little last. So I'm going to call that f at x star, and the star means I'm choosing that x somewhere in that interval. And here I'm choosing it on the left-hand side of the strip, where it intersects or where it meets that curve. And so when I calculate my area, I'm going to just add up those 4 areas, and so I get 0 times 1/2, which is this first column, 1/4, which is the y value right here, times 1/2, which is the width, and then the height of this column is 1 times 1/2, height of the last column is 9/4 times 1/2, and so we have this series going on. And so if I'll just label these as my 4 areas, I'm going to call this my left sum, okay? And so if I calculate those out, I get 1 3/4. Now this is lower. Remember what the actual area is. It's 2.67. It's lower than it because, of course, it's underestimating. We're not getting these areas that are white in our calculation. So we have a couple different strategies that we can use to get a better approximation. Now we can choose a different point, so maybe make the midpoint of this thing go up to here, okay, and then we're going to be a little bit hanging over and overestimating the left half but underestimating the right half of that interval. That's a solution. Or we can simply increase the number of intervals that we have. So instead of just using the width of this as 1/2, we can make the width of it as 1/4, and then our last column will be a little bit taller. So let's look at using more strips first. I'm going to call that L sub 8. L standing for, I'm going to use the left-hand side of that strip. 8 means I'm going to use 8 of them. Okay, so first thing I need to do is calculate what are my values on those strips where it meets the corner here. So like if I'm looking at where 5/4 is, that's the height of the what is that, the 6th column. And so I'm just calculating x squared, which will give me those values. And if I calculate my sum then, I multiply it now, the height of the rectangle times the width. You see, so 0 is the height of the first one, and we're at 1/4. The second one is 1/4 high. We're going to multiply that by 1/4, and so on. I think I left one out. No, I guess I skipped over when I was describing it. The first one is going to be 1/4 high, so we're at 1/4, so that's going to be 1/16 high. The second one is going to be 1/4 high. Third one's going to be 9/16 high. And so when I add all these things up, I get 35/16, and so 35/16 is 2.1875. So a little better estimate, right? So it would make sense that the more of these that we use, the closer we'd get to the actual area. So let's not use the right side, or let's not use the left side. Let's use the right side with 8 different intervals again. And now, since I'm taking the right side of the interval, I'm using this value. So this is my the height of my 7th interval. Remember, before, the height of my 7th interval was this side of the interval, was like this. So now I'm going to expect that I might have a similar kind of quality estimate, but instead of being below my true value, I'm going to be kind of above it, right? So I'm going to use the values that I had before and add all those up to get my right sum. And numerically, that's going to come out to 43/16, which is 2.6875. So I'm a little bit more. I'm a little bit over. And if I compare that to my left sums, L8 is lower, R8 is higher, because remember my actual area is 2.667. Now in this case, it looks like, and I may have made a computation mistake, because something tells me that I'm more than 2/100ths over that. But nevertheless, it's taking the right-hand side of the interval as the height, and then we multiply it by the number of intervals. Okay, so let's look at this from a more theoretical standpoint. So the more I get of these, all right, the finer of an estimate I'll get. And so ultimately, I'm going to get really, really close to my true value. So if I have the number of these strips, and we can call these partitions, or we can call them anything that you want. Partitions is the one that's normally used when you start talking analysis and that kind of stuff. The more we get, the closer we'll get, all the way to the point where if we have infinitely many, we should have the true value, or we should approach the true value. And so you would expect the right and the left sums for the same number of intervals as they go to infinity to be equal. So anybody remember there's a theorem that will tell us something about this here? Okay, so it's going to equal the area. So remember the squeeze theorem. The right sum is always going to be a little bit above, the left sum is going to be a little bit below for this function. Now if my function was shaped the other way, if my function was like this, and it's decreasing, and this is my the interval that I'm interested in right here, my right sum is going to be below, or my right, the height using the right part of the interval is going to be below. The height using the left part is going to be above. And so this above and below characteristic depends on whether the slope is increasing or decreasing. And in fact, if we have one that both increases and decreases, you really can't tell which one is going to be the better one, the left or the right sum. But if we go to infinitely many strips or infinitely many partitions, it's going to equal the area anyway. So it really doesn't matter which one we use, the left or the right. Okay, so let's find this from the standpoint of some calculus now. All right, so my interval is 0 to 2, and I'm going to make a bunch of these strips. I'm going to have n strips, and so the width of these strips is going to be 2 divided by n, right? Remember when I had L4, I had 4 strips, and so 2 divided by 4 equals 1/2, so each of those strips were 1/2 wide. When I had 8 strips, it's going to be 2 divided by 8, so those were 1/4 wide. So I'm nothing fancy here. All I'm doing is I'm taking, what my width of these strips here are going to be. Once I designate, I'm going to have n strips. Now I'm going to use the right-hand side of this interval here. And so x at the 5th strip is going to be 5 times 2 over n. And so here the right side is going to be a little easier computationally, because if I look at where these intervals are going to happen, if this thing is n over, or it's 2 over n wide, this first one is going to be at 2 over n. The second one is going to be at 2 times 2 over n. The third one is going to be at 3 times 2 over n, and so on, until I get all the way to my nth strip, my nth point. That's the n point, so it's going to be n times my width, which is 2 over n. So this is just going to be 2. I'm going to end up at 2. So this is a convenient pattern to decide, okay, I'm going to calculate f at x. What x? Well, I'm going to use the right side of my interval. So that's going to just be, my x value is going to be this 2 over n, or for the 5th one, it's going to be 5 times 2 over n. So the right side gives me the value of the height of that strip. And since the area of any strip is going to be the height times the width, and that's, I'm using a little bit different notation here. This is the height of the function, and this is the width of my strip. For the 5th strip, this is what it's going to be if for any number of strips that I use. The 5th one is going to be like this. And so if I add up all of my strips, and so here, there's the first one where I'm taking the first value of x is 2 over n. I'm going to square that because that's my function, is x squared. Multiply it by its width, so there's the first strip. Second strip is going to be the second value, that's what I was talking about here, where it's going to be 2 times 2. The third value is going to be 3 times 2 over n, and fourth value, and so on. So I'm going to set this thing up. Now I actually drew out the 5th one, but let me add the 6th one, and I'm going to do that until I get all the way to n. So I have this long sum now. And so if I notice that I can factor out, in any of these, I can factor out the 2 over n, and I'm going to have an n squared in each one. So I'm going to factor out n cubed. You see how each of them have n cubed. Each of them have 2 cubed. So I'm going to get 2 cubed over n cubed for every term, and then the only thing that remains is the strip number. So this is the first one, second one, third one, fourth one, and notice all those things are squared, so I have this sum of the squares. Now perhaps you remember from high school there are formulas for the series. So when you add up all the numbers from 1 to, let's say, 100, there's a formula for that. So it's going, and then there's also a formula for the sum of the squares. And so I'm just going to pull this out of an algebra book that you can find, and in fact, if you take calculus far enough, you might even get to the point where you're proving this, where this is the formula for that series. So if I put it all together, my right sum is going to be this. So for any number of intervals I can put it into there and I'll get what I'm going to get with the right sum. And if you don't believe me, you can try it with, I think we explicitly calculated r sub 8. So if we put an 8 in there, we'll find exactly what we got when we did it manually. So let's take a look at it from a calculus standpoint. So if I simplify this thing, notice I can cancel out one of my n's, and then I have 2 cubed is 8, and then my 6. So I basically end up with a simplified expression here. So let's see what happens when we take n to infinity. All right, so you know how to do this, right? How to find that limit. Okay, so we're going to look at this from the standpoint of some factors. So if I just group things a little differently, split up that n squared to be n plus 1 over n times 2n plus 1 over n, what does this thing equal as n goes to infinity? Remember? Polynomial, same degree on the, it's going to be 1. It's the ratio of the coefficients, right? Where it's the same degree, so it's n plus something over n. So you have, as that goes to infinity, our asymptotic value there is going to be 1. So what about here? What is that going to equal? 2. And so my I have the first coefficient, 8/6. The second term is going to be 1. The third term is going to be 2. And so what do I get is 8/3, which is exactly what I got, which is exactly what I said at the beginning, what that area is. Okay, so let's generalize this. That was one particular sum, but we're going to have this for arbitrary functions. And so what I'm going to call this is the width of those intervals is going to be from the beginning of what I'm interested in. Remember, we started at 0, but we don't have to start at 0, to the end, divided by the number, and there's my width. And so if we go back to the one that I did, the width of my interval was going to be 2 minus 0 over n, that 2 over n. So there's my, there's the width. I'm going to have the height of that strip is f at x sub I, and the sub I means for whatever strip, the first strip, I equals 1, for the fifth strip, I equals 5. So I'm going to take a series of just all those values of x, and so any given strip is going to have this area where I'm going to take the height of it times delta x, which is the width of it. So that's my rectangle. And so I'm going to sum them all up. Okay, so summation notation. Have we done that before? Have you seen that at all? Do I need to go over summation notation?
Yes.
How many yeses? 2, 3, 4? Yeah, okay, enough of you. All right, so let's go over what this means. Okay, that funny looking thing that oftentimes when people write and they want to look Greek, they'll use that, what's called a sigma, they'll use it as an E, but in fact it's not an E, it's a sigma. It's the capital sigma, which is the Greek equivalent of S. Okay, so the S stands for sum, and that's where this sigma comes from. So I'm going to take the sum from, this should be, I need to correct this. This is actually, whoops. This should actually say 1. So I'm going to take all my intervals from 1 to n, and I'm going to add up all these values. So if I were to just do this, what this means is that this is going to be 1 plus 2 plus 3 plus all the numbers up to n. And so this is the upper bound here. So if this was like if that was a number like 3, I would stop there. And that's all that means, is that I'm going to take all these terms. And so when I have the area of my strip, so my ith strip, so this could be my first, second, third, fourth, fifth one, I'm going to take all of them and add them together. And that's what this notation means.
The whole thing or just that one part?
Well, this whole thing now means I'm going to take the sum of all the individual strip areas. And so I'm going to have the area then of the total, my estimate under the curve. And so that's for n spaces. And remember, if we take n to infinity, we have the actual area. So let me write this a little nicer. We remember the Riemann sum, or not, I'm sorry to introduce that term right now. The right sum and the left sum, as n goes to infinity, are equal. And it doesn't matter where we choose our x, if it's on the right side or the left side, it's just somewhere on that interval, and as those intervals increase to infinity, that x is going to be the same, right? When I have a very, very small or very narrow rectangle, the left side and the right side for my function are going to be very, very close to the point where when I have infinitely many intervals, these are infinitely narrow, and so these values become the same. So we just denote this as x sub I star. And so if I take that earlier sum, where's my delta x in here? I need a delta x. So this sum here is called a Riemann sum. It's named after a mathematician, of course. They don't name these things after philosophers. Named after the mathematician who first articulated this. And so we're going to be dealing with this Riemann sum in defining what an integral is. All right, now I suppose at this point this kind of feels like that lecture that I gave for the very first class here, where we were talking about all these delta x's and the limits as the delta x goes to 0 for the slope of the line and all that kind of stuff. I would imagine that this has kind of a similar fog factor right now. Wednesday we're going to revisit this, and I'm going to post an exercise for you this afternoon where you're going to actually calculate the area under a curve. So it's going to be one big problem for Wednesday. But do it as carefully as you can, and hopefully you'll get what this notion of right sum, left sum, and what the meaning of a Riemann sum is then by doing that exercise. Okay? And I'll make the corrections so it'll clean up the charts and things. The lecture will be posted as it usually is. Okay?